Now, in this video, we're going to talk about the concept of resonance. This is a very nice concept. But before we do so, we have to introduce a couple of terms. So let's start off with something called a forced oscillation. So a forced oscillation is one which is created because of something called a periodic external force, right? And so a periodic external force is precisely what it sounds like. It's a force that hits something periodically, a little bit like someone tapping the drum, right? You hit the drum periodically. And of course, we want to introduce another term called the natural frequency of a system, and that is the frequency anything, right, that you want to define as your system vibrates at naturally if you don't do anything to it. So everything in this world has its own natural frequency, including you and me. All right, it's just that sometimes you don't see it because the amplitude can be quite small. Now, to put all this into context, this forced oscillation or the periodic external force, if I put it into the context of a swing, is basically this guy over here who pushes his friend on the swing every time the swing comes to this position. While the natural frequency of this swing system will be simply the frequency of this swing, right, as it goes back and forth like so. Now, when you push your friend on the swing, of course, you always try to push your friend when he comes back here. And so without you thinking too much about it, you are actually allowing the frequency of your periodic external force, let's call that the driving frequency, you're allowing that to match the natural frequency of your system, which in this case is the swing. And when this happens, we get the concept resonance. All right? Every time you push, when the swing comes back, you're injecting energy into the swing. And so when you allow Fd to equal to F naught, we say that there is a maximum transfer of energy from the periodic external force to the system, and therefore this causes the amplitude of the system to increase to a maximum value, increase to some maximum value. Now, this maximum value can be very, very large. In fact, what we're going to do now is we're going to plot a graph of the amplitude of a system together with its driving frequency. We call this a frequency response curve. And if we allow Fd to equal to F naught, the natural frequency of the system, I'm actually going to draw an asymptote here, and your graph looks something like this. If Fd equals to F naught, your amplitude tends to infinity because you keep injecting energy to the system, and so the amplitude keeps growing. There is no reason why it should stop. Well, actually, there is. So this is what happens when there is no damping. So there's no energy loss in your system. Now, what happens to your graph if you do introduce damping? So this is very important, the effects of damping on your resonance. Well, first of all, you will have a finite peak. And also, you'll find that this peak shifts left. And so, for example, with some damping involved now, the graph may look now something like this. So see that my amplitude is lower for every single value of Fd, but also now I have a finite peak here, and it's now a little bit to the left. And so every time I increase the damping, the graph gets a little bit more flat, like so. Again, you'll see the peak decreases, shifts more to the left, and so the process continues. The reason why your peak shifts left, right, is because when you damp a system, the natural frequency of that system decreases slightly, okay? And so this is consistent with what we mentioned in the damping video when we said that the period of a system under some damping may increase a little bit. So this is how your system's frequency response changes with increased damping, okay? And so finally, some useful uses of resonance. You may want to take this down, right? You use it sometimes in microwave ovens and also in radio transmission, or should I say radio tuning.